And welcome back. As we move into our next review lesson, let's go ahead and discuss now inverse functions and logarithms. So to start us off, we first need to discuss the idea of a one-to-one function. If you recall, a function is a rule that assigns a single value in its range to each point in its domain. Now, some functions assign the same output to more than one input. So if we look at the example of the function f of x equals x squared, it assigns the output for both to 2 and -2. And if we think about it, that's because when we graph this function, we have this parabolic shape where if we were to look at those 2 points here, so if I go, let's say here, make a rough, quick view of this, we're going to have this point be able to repeat over this parabola. Now, other functions never output a given value more than once. For example, the cubes of different numbers are always different. Think about a cubic function. Those are going to be much different in their approach here. So they're going to have something like this. And if we look at this, each of these out values of that function are associated with exactly one input value. And so we can say it's a one-to-one function. And our definition states that a function f of x is one-to-one on a domain if f of a does not equal f of b, wherever a does not equal b. Here, of course, you can see that this is an example of a not one-to-one function, and this one is an example of a one-to-one function. And if we look at the graphs again of a one-to-one function, y equals f of x, can intersect any horizontal line at most once using the horizontal line test. If it intersects such a line more than once, we assume the same y value more than once, then therefore it's not 1, 1. So if I go ahead and let's go ahead using these two examples, if I draw a horizontal line through here, you can see it passes through more than one point, so it would fail the horizontal line test, so it's not a one-to-one function. Whereas here, it doesn't matter where I put that horizontal line, you can see that we're always only going to have one point of intersection. So let's go ahead and take a look at this and say, okay, we got two different functions here. I have f of x is equal to the absolute value x, and g of x is equal to the square root of x. I'm just going to go ahead and pull up my calculator here, just go ahead and put those in just so we get a nice quick representation. And again, we want to do the absolute value of x, and then we're going to do the square root of x. And let's just go ahead and do a standard zoom here. And so we have our absolute value function, which the standard V formation, and then the square root is kind of more of this curve. So I'm just going to go ahead and real quickly sketch those back onto here just so we can get that. And we're going to use the horizontal line test to really kind of help us determine this. And so I'm going to use that for f of x, and let's use this red for our g of x. So this is g of x, and this is f of x. So when we look at these two functions, let's do a horizontal line. So let's do a horizontal line through f of x, and you can see we have 1, 2 points. And when we do that same line now, let's do a green one here, for g of x, we only have 1 point of intersection. So if we look at this with f of x, we can say that f of x is, so for part A, we can say that it is not one-to-one. And for part B, we can say that it is one-to-one. Now, of course, when we start talking about this naturally leads us to our other topic, which is that of inverses. Since each input of a one-to-one function comes from just one input, a one-to-one function can be reversed, and you can send those outputs back to which they came. The function defined by reversing a one-to-one function we refer to as the inverse of f. All right, the symbol for the inverse of f is this f minus 1, which is read as f inverse. Now, please note that that minus 1 here is not an exponent. So it doesn't mean f to the power of -1. It's simply just a notation that we use to represent the inverse. Now, if we compose a function with its inverse, so f of the inverse of x in either order, which is going to send each input back to the input from which it came. So in other words, the result of composing a function and its inverse in either order is an identity function. So another way to think about this is if you say f composed with g of x or g composed with f of x, either way, if you plug those in and we get x as our ending value, then f and g are both inverses of each other. So when we talk about finding inverses, it's okay to know that property, but how do we actually, like, for example, find the graph of the inverse function? Well, the graph of our function f is already the graph of our inverse function, although the ladder graph is not necessarily drawn the same way with the domain axis and horizontal range. So for our inverse function, we flip those input and output pairs. And if we want to really think about writing that as a function, we're going to solve the equation y equals f of x for x in terms of y, and then what we do is you interchange x and y and get a resulting formula y is equal to the inverse of x. So with that in mind, let's go ahead and try to find ourselves an inverse function. So we have the function y equals f of x, which is equal to negative 2x plus 4. And we know that this is already a one-to-one function, so that's important to note because it has to be one-to-one. And we want to find its inverse function. All right, so if we want to show that it's one-to-one, the first thing we want to do here is we want to make sure that every horizontal line that intersects the graph f, it happens exactly once. So we are going to first say, let's solve for x in terms of y. So we're going to rewrite this. So we can start off with y equals a negative 2x plus 4. And if we want to solve this for x, well, we can simply subtract 4 on both sides. So we get negative 2x is equal to y minus 4. And if we divide by negative 2, we get x is equal to 1/2, negative 1/2, y plus 4. Oh, plus 2, sorry, forgot to do the division there. All right. Now that we've done that, we can then interchange our x and y to help us find the inverse function. So if we want to find that inverse function, what we're going to do is take this original function here, and we're going to switch x and y. So I'm going to take this, and I'm just going to rewrite this as y is equal to a negative 1/2 x plus 2. All right. So if we want to prove that this is an identity, then what we need to do is effectively take the inverse function and the function and compose them into each other. So what I'm going to do is say, all right, let's take f of the inverse of f and f of those two pieces here. And the way we can say, okay, well, we're going to plug those equations into each other. So we are going to have a negative 1/2 of we're going to, again, plugging in this original equation now. So negative 2x plus 4 plus 2. And we can then do some simplification here. So this is going to simplify to x minus 2 plus 2. And of course, when we look at this, we have two terms that can cancel right out here. So this cancels out. And so then we just have this equaling x. All right, so that verifies on this side. And if we work it the other way, so if we say f of our inverse function of x, this is now going, of course, going to allow us to do the same thing, but in reverse. So we're going to take our original function, negative 2, times our negative 1/2 x plus 2. Right. And when we distribute that through, we are going to get a very similar approach, except we're going to end up with x minus 4 plus 4. And again, just like before, we can look at this and say, oh, these are going to cancel out. And we are going to end up with our final value of simply just x, which again tracks. So because these are both x and x, we know that this, of course, maps to being 1/1, because remember, this is an identity here. And of course, this is our inverse function right here, because we simply just were able to interchange those values. Now, what about if we had a graphing something parametrically? Because here we have a 1/1 function. We have f of x is equal to x squared for x is greater than or equal to 0. And its inverse, and the line y equals x for x is greater than or equal to 0. All right, and we want to ultimately express the inverse of f as a function of f. So what we want to do is actually start off by graphing these various functions. So I'm going to go ahead and head to my calculator. And let's go ahead and make sure we have the correct mode here, because right now we're in function mode, so we want to switch over to parametric. Go back to my y equals. All right. And so we have, of course, a couple different functions. So let's start off first with our graph of f. If you remember, our graph of f was x squared. So with our graph of f, we can say that x1, we're simply just going to set that to t. Our y will be equal to t squared, because that's our x squared function here. And we want to, of course, set our range. But let's go ahead and, while we're right here, set up our other functions. So we have the graph of f to the inverse. So that is, what is the inverse of this function here? Well, the way we can set this up is, remember, we're switching the x and y values. So this will be t squared, and this will simply just be t. And then for our final function, which we said was y equals x, we are simply going to come down here into our third value and simply just put t for both of these. Now that's all set up, let's adjust our window value here. We want the window to, of course, we want our t min to be 0. That's good. I'm going to actually just make this 10 just so we can see a nice good value. And set a t step to 1. And let's go ahead and just graph that function. Now you can see we have, of course, these three functions here. I can actually bring that window down a little bit too here if I want to. Let's just go ahead and just make this 0. Just so we can bring that in. And let's make our y value starting at 0 as well. So go ahead and graph it. And so you can see we have the three different functions here now graphed over this. So this is the three graphs that we want to do. So we could easily transpose this sketch over into its own image. But what we want to do after we've done this is find our formula for the inverse function. And how can we find a formula for the inverse of this function? Well, the way we can go about doing this is we want to solve for x in terms of y. So let's start with our original function, y equals x squared. So that is our original. So we want to rewrite this. So the easiest way to do this is I want to solve for x, square root of both sides. And so now I have the square root of y is equal to x. All right. And if I want to do this further, I could, of course, do this as saying like x is equal to the square root of y, or I could even say that is equal to y to the 1/2. Either way, this is still a very good idea for what our inverse function might be. Now, if we want to interchange this and put it into that actual inverse function, so we can say that the inverse function of x is then equal to what? Well, going back to here, we have to remember interchange our values. So we had x is equal to the square root of y. So we want to interchange that, which means that in here, since x is equal to the square root of y, this is equal to the square root of x. Because remember, we just switch what these two values are to get our interchange. All right. Now the next big thing to talk about, since we're talking about inverses, is logarithmic functions. If you have when we start talking about logs, and we have exponents involved, if a is any positive number other than 1, the base a of an exponential function, f of x equals a to the x, is 1 to 1. And because it's 1 to 1, we can then say it has an inverse. And the inverse is called the base a logarithm function. And what this simply just means is the logarithm function, y equals log base a of x, is the inverse of the base a exponential function, y equals a to the power of x, for when a is greater than 0 and a does not equal 1. Now, domains of logs with base a is starting from 0 and goes up to infinity, which is, equivalent to the range of our original a to the x function. Now, the range of log base a to the x is from negative infinity to infinity, which is our domain of a to the power of x. Because remember, we are just interchanging those x and y values. Now, because there is no technique for solving x in terms of y in our equation y equals x, or a to the x, we do not have an explicit formula for the logarithm function as a function of x. However, the graph of y equals log base a of x can be obtained by reflecting y equals a to the power of x across the line y equals x, or by using parametric graphing. Another thing to keep in mind is that logs that have either base e or base 10 are important in various applications and are represented with their own special notation and names. So if I have log base e of x, we can just say that is the natural log of x, or the natural logarithm. If I have log base 10 of x, we a lot of times will show that it's just log x, or the common logarithm function. Now, some of the things we're going to need to know when we start dealing with logs is that we have some properties that we can use to make our life better. Because a to the power of x and log base a of x are the inverses of one another, composing them in either order gives an identity function, which gives us some really useful properties. So if the base a is greater than 0 and a does not equal 1, a to the power of log base a of x is going to simply just give us x for any x that's greater than 0. And log base a to the power of a to the power of x for all x. Now if we do this with e, and we say e to the power of natural log of x equals x, we're going to get the same thing, just for x is greater than 0, and natural log of x equals x for all x. It's some pretty cool, handy stuff that makes our life a lot simpler. So let's go ahead and apply this now using some inverse properties to solve two different examples. So our first one here, if we take a look at it, is going to give us, we want to solve for natural log of x is equal to 3y plus 5. And then our second one is going to be e to the power of 2x equals 10. So let's go ahead and solve letter A first. So we have the natural log of x is equal to 3y plus 5. All right, and so what we want to do is solve this. Well, if you recall, we have a natural log here. How can I get rid of a natural log? Well, the inverse function is going to come in handy here. So I'm going to use the inverse of the natural log, which in this case is saying e to the power of something. And so if I say e to the power of the natural log of x, and then of course if I do it to one side, I have to do it to the other, it's then going to equal to e to the power of 3y plus 5. Okay. And now I can go ahead and say, oh, this is an inverse, which means that this part right here can cancel, leaving me then back to the value x equals e to the power of 3y plus 5. All right, and of course, all we want to do is solve for x, so this works. Now for part B, let's do e to the power of 2x equals 10. And again, same thing as before, what we want to do is use our inverse properties to help us solve this out. So if we know that this is e to the power of something, I can then instead say, you know, let's take the natural log of e to the power of 2x and set that equal to the natural log of 10. All right, now that I know this, I can then, of course, see, oh, I have something that can cancel out. This natural log and e will both cancel out. And that's going to take me back down to 2x is equal to the natural log of 10. But, of course, I can't just leave this x alone, so I need to divide both sides by 2. And so we should get that x is equal to 1/2 the natural log of 10. Now, unlike our first value here, which is, you know, a nice kind of more algebraic expression, this one we can actually evaluate. And if we evaluate this and plug in our calculator, we'll find it's about 1.15. Right? But either way, these are, of course, our nice values that we can then work with and use these properties to help us solve. Now, the logarithm functions are very useful, and they have some properties that can make our life a lot easier when we start encountering them. So when we look at the properties of logarithms, if we have any real numbers, x is greater than 0 and y is greater than 0, we can use 3 different rules to help us. The first is the product rule. It simply says that log base a of x times y is the exact same thing as log base a of x plus log base a of y. So we can just take that and separate out this quotient or this product in here. Similar thing happens with the quotient rule. We have a log base a of x over y. We can separate that out to log base a of x minus log base a of y. And we have a power rule that says, hey, if we have log base a of x to the power of y, this y here that exists can actually be moved, and we can rewrite that function as, or expression as y log base a of x. So these can come in real handy here when we want to, of course, take something that might look really complex and make it a lot simpler. And if we want to say, hey, you know what, we have something that we want to maybe evaluate differently. So for example, we have a log base a of x for any base a where a is not 0, and want to obtain its graph. Well, we can use the natural logarithm function for our grapher. So if I have log base a of x, this is the exact same thing as saying, hey, take the natural log of x divide that by the natural log of a. And let's apply that to an example. We want to graph the log base 2 of x. Well, let's use this change of base formula here to figure out what we actually need to plug into our calculator. So we know that f of x is equal to log base 2 of x. So if we rewrite that using this rule, we know that's the same thing as the natural log of x divided by the natural log of 2. And then that should allow us to be able to take this and plug it into our calculator. So I'm going to go ahead and pull our calculator back up, turn it back on. I'm going to change my mode back to function because this is going to be a function mode, and clear out our existing functions here. And let's go ahead and set this up. We want to do the natural log. So I'm going to hit the ln here and do of x, close that parenthesis, and do a divide by the natural log of 2. And let's go ahead and set our zoom to standard here just to see how this looks. And you can see here is our function right here. So this is the log base 2 of x, or the natural log of x divided by the natural log of 2. Now, logarithms are really, really useful, and we can use them in many different ways. One of the ways that we can use logarithms is to solve exponential growth and exponential decay algebraically. And here we have an example of a compound interest problem, but we're going to be using logarithms to help us out. So here we have Sarah investing $1,000 in an account that earns 5.25% interest compounded annually. And the question here is not how long is it going to be after how many years, it's saying how many years is it going to take for that account to reach 2,500. So this is going to take us back then to think about, okay, how can we set this up? Well, the very first thing I want to think about, okay, is this is my principal here. So we know the principal is $1,000, and we have our interest rate is 5.25%. And our goal is to hit the 2,500. So the amount, so the end value is 2,500. So what we want to do is then use these and rewrite it into an expression or an equation that we can solve. So let's say we have $1,000 times, and we're going to use for this one, in case you haven't figured out, we're going to try to use compound annually. So it's principal times 1 plus our rate. And since it's annually, we don't have to worry about anything to the power of t. Is going to, of course, give us our total value. So 1 plus r, we can just simplify that instead of saying 1 plus the 0.05. I'm just going to go ahead and simplify that to 1.0525. So in case you're wondering how to get this, remember it's just 1 plus the interest rate. And we don't know our time. That's the one thing we don't know. But we do know that the ending value is 2,500. So with this in mind, we can go ahead and solve this and try to come up with a value that can use it. Now, again, we're going to need to use logarithms here, but we can do a little bit of algebra here first to kind of help simplify this. So for example, I can look at this and say, oh, well, I can get rid of this 1,000 right off the bat. So let's divide by 1,000 on both sides. And so with that out of the way, I can then simplify this to 1.0525 to the power of t. Is then set equal to 2.5. Now I have an expression where the logarithms can come in handy. And because we want to evaluate this, let's go ahead and just use the natural log to simplify both of these. So what I'm going to do is I'm going to take the natural log of both sides, and I'll do a natural log here. And now that there is a natural logarithm here, I can also know that using my exponents rule, because I have something that's to the power of it, I can move this t outside of that expression. And so let's go ahead and move that t outside the expression. And so that becomes t natural log of 1.0525 is equal to the natural log of 2.5. And now it's simply just a little bit of solving for t. So we're going to divide both sides here by the natural log of 1.0525. That part cancels. And so then we can solve for t, and we can plug that in and find out that t is simply going to be approximately, I'm going to actually make that more of an approximate because it's not an exact value here, but we're going to say it's approximately about 17.9. Now that 17.9 is, of course, in this case, because we're doing annually, we need to make sure for our units on here, this is 17.9 years. So it's going to take about 17.9 years, or if we want to think about that, that's about 17 years and about 9 months. So it's a pretty decent chunk of time for it to go from 1,000 to 2,500.